Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we are going to be examining electrophilic addition to conjugated dienes. Up to this point, we have been examining the reactivity of alkenes and focusing on reaction when there is only a single double bond in the molecule. But equally important is the behavior of the carbon-carbon double bond when it is conjugated to other carbon-carbon double bonds. Now, what we want to do here is begin looking at the molecule 1,3-butadiene and its reaction with HCl. In this case, the electrophile H+ is attracted to the pi cloud, and we will get Markovnikov addition. Because Markovnikov addition will lead to the most stable double bond, most stable carbocation. So once we add our H, we'll add it here to the CH2. This produces a secondary carbocation, but not just any secondary carbocation. It is a secondary carbocation that is resonance stabilized. That is, I can move these pi electrons this way, and I can draw a resonance contributor. Now, if you remember correctly, you know resonance contributors don't exist. What exists is the resonance hybrid. The resonance hybrid is some average combination of both resonance contributors. In this case, the resonance hybrid would look something like this. Where the pi bond is delocalized over 2 carbons, and the delta plus is spread out over these 2 carbons. This is what the incoming nucleophile, the chloride, will see. So when the Cl- attacks from the HCl, it will be attracted to both positions. Which product will form will depend on the energetics of the reaction. In this case, temperature plays a very important role. So if I add it to this position, that is, it attacks if I add here, it attacks the top resonance contributor, I would get this product. Where the H added here, the Cl added here, and hence the term 1,2 addition. Likewise, the nucleophile could attack at the end. If it does, I'll get this product. And since the H+ added here and the chloride added here, this is referred to as 1,4 addition. So 2 products are obtained. They're formed from electrophilic addition that yields a resonance stabilized allylic carbocation that is then attacked by the nucleophilic portion of the molecule, in this case Cl-. Now, if I were to represent these molecules in a potential energy diagram, I would start with my reagent, which is the diene. So this is my conjugated diene. I'll just write diene here. This is energy, remember? And this is progress of reaction. Sometimes it's just called time, increasing that way. Now the diene has an energy of activation, H plus adds. And then we hit a valley right here. Now, I'll level that off a bit. What's in this valley? Well, this is the resonance. Stabilized. Carbocation. Resonance stabilized carbocation. Okay, it's this guy. If I was drawing it from the previous, would be this molecule. Delta plus, delta plus. Now it's at this point we get a deviation. Okay? We get a deviation. And let's consider what products we're going to make. Let's consider the 1,2 addition product, which is this guy. Wonder if I can make him. Running out of room. Ran out of room. So here's the 1,2 addition product. Oops. Put the Cl in the wrong position. Compare that to the 1,4 addition product and think of which double bond is more stable. So here's the 1,4. The 1,4 addition product I'll label as, let's use different colors. Let's call the 1,4 addition product black. Here's A. And let's label this guy as B. And, oh, we were supposed to use different colors. So here's B. Now here's the interesting point. Who is more stable? Who is lower energy, A or B? Well, if I remember the Zaitsev rule, which says the most stable predominates in this major, that doesn't help me. But the rule that indicates which double bond is more stable comes from heats of hydrogenation. And heats of hydrogenation show that the more substituted double bond was energetically more stable. So all you have to do is look back in the scribblecast dealing with heats of hydrogenation to see how experimentally the stability is determined. But we learned in this course that the more substituted double bond is more stable. This double bond, A, has more substitution, has two alkyl groups, whereas B only has one alkyl group of it. So A is lower energy. So here's A. And B is higher energy. Now most of the time you'll get the higher energy, less stable product to give you the less stable transition state. So you would usually get something like this. And then if I was to draw the black line for the black, many reactions are like this, and usually that's when you take the lower energy pathway, the more stable product predominates, and A would be major. But sometimes, on rare occasions, that isn't the case. And in this case, that does not happen. It turns out the more stable black molecule, labeled A, has the higher energy of activation. Now we're not going to, while it's not intuitively obvious why this would be the case, we'll just accept that for the moment. And the less stable product, the 1,2 addition product, has lower energy of activation. This leads to what I call crossover in the potential energy diagram. Right here. I call this crossover. In the potential energy diagram. This is a potential energy diagram. So let's put it in the PE reaction diagram. Crossover in the potential energy reaction diagram. Often when we draw these types of diagrams, we actually draw the curve from here. And the reason being is we're only interested in what's going on in this pattern because this part's pretty basic. There's the path is identical for the generation of the carbocation. It isn't you get two different paths until the carbocation is attacked. Now when you see crossover in the potential energy diagram, this leads to the rare phenomenon of possibly having two different products distributions based on temperature. Or that as you vary temperature, you'll get the different products being major. The percentage composition of who is major will change with temperature. Why would that be the case? Well, let's think about the red situation first. The one with the low energy of activation. Here's the energy of activation, okay, for the less stable 1,2 addition product. Because its activation is so low, at low temperatures, it will be easier to get over this energy of activation than it will be able to get over the black line because it has a greater energy of activation. That energy of activation is larger. So at low temperatures, more molecules follow the red path than the black path, and B predominates. At extremely low temperatures, the reverse path is not possible. The energy of activation for the reverse, going backwards, measured from here. Okay, I'll use the different color again. Here's the energy of activation for the reverse path. That's huge. So at extremely low temperatures, you can't go backwards. So once you're over this hill, you're stuck, and more molecules make it over to B, which is red, than to A. So at low temperatures, B will predominate. So let's write that down. So at low temperatures, B predominates, because more molecules make it over the low hill than the large. So B is major. But what happens as you raise temperature? Initially, very little. There may be some change, but as you begin raising temperature, more and more molecules start getting enough random kinetic energy to follow the reverse, overcome this green energy of activation arrow. Now, what's interesting is the reverse. Oops. The reverse energy activation. Oops. For the red guy is smaller. So as you raise temperature, molecules start going back. As you keep raising temperature, some black molecules will eventually overcome its reverse energy of activation. And you start establishing what's in equilibrium as you raise temperature. Now, more molecules will go backwards from red B because it has a lower reverse activation energy than going back from the black because it has the higher. So a few molecules make it over the black hill, but fewer get back. And so black A starts building up in concentration. Molecules keep going back to the carbocation from red B, and some of them make it over the black hill. Eventually, as you keep raising temperature, black A will start to predominate because it's more stable. So under equilibrium conditions, where you have enough energy to undergo the reverse energy of activation, B starts going back more often. Few molecules make it over the black hill. They tend to sit and accumulate, and black A begins to predominate. At high temp, A becomes major. Now, A, remember, was what we called the 1,4 addition product. B was the 1,2 addition product. When you're at low temperature and the energy of activation for it is controlling the reaction, you are said to be under kinetic control. Kinetic control. What is a kinetically controlled reaction? Well, remember, kinetics has to do with rates, how fast the reaction goes. And what determines how fast the reaction can go? It's the size of the hill. So if the size of the hill is controlling which product's major, since the size of the hill controls the rate, or the kinetics, the reaction is said to be under kinetic control. Low temperature, where the 1,2 product predominates, is called kinetic control. The high temperature, we're establishing an equilibrium. So this is sometimes called, and I'm going to just use EQM for equilibrium. EQM meaning equilibrium. Equilibrium control. Because what's happening is we've put in enough energy to not only go forwards, but we've raised temperature high enough so we can overcome the reverse energy activation, the green lines. And because the biggest hill, forward or backwards, is the black hill, backwards, the A, 1,4 addition product, begins to predominate. So this is called equilibrium control. It is also sometimes called, because A is the more stable, and that is according to delta H, and delta H is thermodynamic value, it's sometimes called thermodynamic control. So you can call equilibrium control or thermodynamic control. Now this happens at higher temperatures and the 1,4 product becomes major. So in a thermodynamically controlled reaction, you have an equilibrium established and the more stable molecule predominates. Under kinetic control, you get kinetic control at low temperatures where you don't establish an equilibrium, and in this case, the less stable predominates. These two types of control are possible because there is crossover in the potential energy diagram. If this crossover did not occur, that is, the smallest of energy activation had the least stable product, and the largest energy of activation had the more stable product, causing them to cross over like this, then you don't get this temperature dependence. So whenever I'm given a potential energy diagram that I see crossover like this, I know, uh-oh, there may be temperature dependence, and I have to watch for a kinetically controlled reaction and a thermodynamically controlled reaction. Well, what happens? How does this bear itself out in a real reaction? Let's give you a real-world example. And instead of HCl, I'm going to use HBr. I'm going to react it with butadiene, 1,3-butadiene. So here's 1,3-butadiene. And I'm going to react this first at low temperature. Let's try minus 80 degrees C. And then I'm going to also react it at plus 40 degrees C. Right. At minus 80 degrees C, the temperature is low. And, you know, when you're given this type of question, if I ask you to explain it, you'll be given two temperatures, and you will have to predict which product is major and which is minor. Now, for this conjugated diene, the 1,2 diene is least stable. And at minus 80 degrees, the least stable product is major. So it's the 1,2 addition product. In this case, I'm going to have you memorize this special case, this one example, the temperature and the product distribution. So if we make 1,2 addition product, that is, I put the H here, I put the Br right beside it. This is 1,2 addition. It is the least stable alkene because it is the less substituted. Double bond. This is the most stable product under these conditions. In fact, it's present in 80% yield at low temperatures. This is an example of kinetic control. The reaction is kinetically controlled. Let's look at the 1,4 addition product. Here's the 1,4 addition product, and it's present in 20% yield at minus 80. So this corresponds to the previous slide. If you like, I'll circle them by the colors so you can tell. At low temperatures, the kinetic, the less stable alkene predominates. He's major. Whereas the 1,4 addition product was black. Okay. Now the same products form at plus 40. But what's interesting, at plus 40, the 1,2 addition product, the less stable, is no longer major. The reason, the reaction is no longer under kinetic control. It's under what we call thermodynamic control. An equilibrium is established. And so this guy is now at plus 40, only present at 20%. The (1,4) addition product becomes the major product under these conditions, and now it's present at 80% yield. So just raising the temperature 120 degrees causes a complete reversal in who's the major product. This temperature dependence occurs because of that crossover in the potential energy diagram. And he's major, not the red molecule. So at minus 80 degrees, the reaction is kinetically controlled. Reaction is kinetically controlled. The 1,2 addition product is formed faster due to a lower energy of activation. There's no equilibrium since there's insufficient energy for the reverse reaction. We can't overcome that energy of activation reverse. At 40 degrees, the reaction's under thermodynamic control, equilibrium is established, and there's enough energy to overcome the energy of activation reverse for both reactions. But because the energy of activation reverse for the 1,4 addition product is largest because it's the most stable, molecules begin to accumulate with the 1,4 structure. And as a result, it begins to predominate. So you could apply these two structures to our previous, and I'll draw that again. I'm going to just draw the potential energy diagram underneath to show this. And I'm going to start from the carbocation. So here's my potential energy diagram. Energy increases in this direction. I'm going to start from here. And the black molecule, of course, was the most stable, 1,4, the more substituted double bond, so it's more stable. The red molecule is less stable. It's the 1,2 addition product. The black molecule had the largest energy of the transition state, so it's got the big hill. And the red has the smaller energy. And again, you see the crossover here. Right there. Crossover in potential energy diagram that suggests temperature dependence. Crossover means you have a chance of getting differing percentages with temperature. When you don't have crossover, there's less variation with temperature. And so whenever you see this crossover in potential energy diagram, you've got to watch for kinetic control, low temperature products where the red predominates. The 1,2, because it's the red, low temp. Kinetic control. And of course, the molecule that predominates at higher temperatures, high temp, thermodynamic control. And the more stable molecule predominates, which in this case is the 1,4 addition product. Now, will the 1,4 always be major? Well, usually, because it's a more substituted double bond. The red is the 1,2 addition product. And at low temperature, it's major. So you need to understand the terminology of kinetic control and thermodynamic control, be able to use them to explain product distribution. You should be able to explain these products. And if I give you a reaction, HBr plus 1,3-butadiene at plus 40, you should be able to show is major. This guy at plus 40 is major. You could give the percentages, but you would just have to write at this temperature, he's major. And the other molecule is minor. Okay. Now, chemistry of conjugated dienes is very important. In fact, it's so important that there was a reaction discovered in the 1950s that led to the winning of a Nobel Prize because it allowed for the production of a wide range of organic molecules. And this reaction is referred to as the Diels Alder reaction. Now, the Diels Alder reaction is a different type of reaction. It is a 1,4 addition of a multiple bond to a conjugated diene. In other words, we have a conjugated diene like this. Here's the line formula for 1,3-butadiene. Same molecule I drew earlier, okay, but it's in its line formula. And if I react this with an alkene, I can get a reaction, like ethene. It doesn't just have to be the alkene. I could use, for example, with the same diene, a molecule of ethine. Could use a triple bond. Long as I have a pi system reacting with the diene, I can get this sort of reaction. Now, when the reaction occurs, we get what is called a 4+2 cycloaddition. Let's write that down. 4+2 cycloaddition. So we have a 4+2 cycloaddition reaction. What does cycloaddition mean? Well, it means your product that you form is a ring structure. So cycloaddition means making a ring. Okay, so we're making a ring, a cyclic compound. A cyclic ring. The 4+2 means the reaction involves 4 pi electrons interacting with 2 pi electrons. The 4 pi electrons come from the diene, and the 2 pi electrons come either from the alkene or the alkyne or some other pi system. Because we've used terms like electrophiles are attracted to electrons, nucleophiles are attracted to nuclei of positive charges, we're going to use the term here dienophile. Dienophile is any group that will be attracted to the diene in this manner. And so this is some pi system. Other pi systems that could do it are alkene, alkynes, or molecules that might be like R, N, double bond, N, R. You could for example, use some strange nitrogen pi system as a dienophile. So the alkene-alkyne is the dienophile, whereas the 1,3-butadiene is, of course, our diene. Now what happens? Well, it turns out that the electrons move in a circle. The pi electrons from the alkyne or alkene move towards the ring, but the pi electrons of the diene move in a circle, also towards the dienophile. And so if these two link up here, I'm going to get something that looks like this. And in this case, I'm going to get something that looks like this. Let's draw the new bonds that have formed. So let's draw it again, the same structure, product structure. But this time, I'm going to use blue, and I'll use black for the bonds that have formed. Those are the bonds that have formed. Now, if you look carefully at this, you see what has happened. One of the pi bonds from the dienophiles moved towards this end. I'll put a black dot. That carbon. The pi bond shifts to make a new pi bond, and the other pi bond moves out from here to attack. And so you get two new sigma bonds and a shifted pi. The reaction involves a redistribution of electrons and bonds. Two double bonds are replaced by two new single bonds and a double bond. So we are breaking 3 pi bonds and making 2 sigma in a single pi. The exact reaction is a cycloaddition, means making a cyclic ring. The circular movement of electrons is referred to as a pericyclic reaction. If you see the term pericyclic reaction, it means electrons move in a circle. And you see we get a circular movement of electrons. So we get a pericyclic movement of electrons and a cycloaddition. And students often mix up these terms, so please keep them straight. Cycloaddition reaction is where one reactant combines with another to form a cyclic product. A pericyclic reaction is a reaction that involves redistribution of bonding electrons in a cyclic manner. Electrons move in a circle. Now, it turns out that this reaction can be aided by putting substituents both on the diene and the dienophile. So if we proceed with this next structure, we see the diene with electron substitution groups push electron density, making the electrons in the pi bond more electron rich and more susceptible to attack by electrophiles. This is exactly what we've seen in increasing reactivity in alkenes. So our diene is acting like the alkene. We can increase the reactivity of the dienophile, it acts like our electrophile. If we put electron withdrawing groups, such as cyanide groups, which are very electron withdrawing, the pi system becomes even more susceptible to attack and looking for electrons. It behaves like an electrophile. As a result, we get electron donation from the pi cloud of the diene towards the dienophile. When you put electron donating groups on the diene, and electron withdrawing groups on the dienophile, the Diels Alder reaction speeds up. This suggests that the dienophile is acting as the electron acceptor, because electron withdrawing groups would help it accept electrons. This suggests that the diene is donating electrons from its pi system because the electron donating groups would push electron density. Right? So overall, electron donating groups on a diene will speed up the reaction. We could put electron withdrawing groups on the dienophile. That would speed up the reaction. Putting it on both would certainly speed up the reaction. In terms of stereochemistry, we see that I'm always drawing my diene this way. Well, that makes sense if you're going to make bonds in that direction. But you got to notice that the single bond here, there's free rotation. The diene can adopt this conformation around that. In other words, yes, there's hindered rotation around the pi bond, but where there is no pi bond, there's free rotation. Now, when there's free rotation, you really don't have cis strands, but you've got to admit that seeing the two double bonds in this orientation is this guy sort of looks like he's cis. The two double bonds sort of look cis, and the two double bonds here sort of look trans. But there's free interconversion. There is rotation, and it happens very fast at room temperature. Because they wanted to indicate that this structure is the structure that does Diels Alder. It's got to be in this orientation, this conformation. They wanted to give that conformation a name, and they said, let's call it s-Cis. And let's call that s-trans, where s stands for the Greek word pseudo. Pseudo meaning fake. S-Cis is not really a geometric isomerism because there's free conformational change at room temperature. There's free rotation around the single bond. The S-Cis and S-trans always interconvert. And one could argue that, well, if they always convert, how do you know you need the s-Cis? Well, it makes sense. I mean, if you're going from this and you're adding an alkene to that, where you make your new bonds, Well, you clearly see how these are joined up through the black bonds. You have that pseudo-cis arrangement. The pseudo-trans would have to rotate to a pseudo-cis to react. It's just obvious and it's common sense. Be nice if there was some experimental proof for that. Well, there certainly is if we use a molecule like this molecule. And I'll try to draw it. A molecule that is locked into the pseudo-trans conformation. And in fact, let's do it this way. Now what I want you to focus on, let's try drawing it again using different colors. I want you to focus on this part, the green part. Notice how that is similar to the pseudo-trans. And because that green part is tied together by this ring, in a six-membered ring, it is locked into the pseudo-trans. There's no way you'd have to break the ring to get this green to go cis. Here's a molecule that can't form the pseudo-cis conformation. This molecule, if I was to name it, we learned that carbenes, CH2s, are called methylene. And so the CH2 here, it's blue, is called a methylene group. And so if I number this 1, 2, 3, I have a methylene off carbon 3. So this is 3-methylene. Cyclohexene. And you're responsible for that name now. 3-methylene cyclohexene cannot get pseudo-cis. Hence, it should not be, if pseudo-cis is required to do a Diels Alder, there should be no reaction. If I take this in the presence of some alkene, trying to do a Diels Alder, and I apply heat, by the way, triangle for heat in this system means a Diels Alder reaction. And in fact, usually you have to put heat to get a Diels Alder reaction. You get no reaction because this molecule can't go pseudo-cis. So this is proof, if you like, or evidence for the requirement of the pseudo-cis. It's not really proof because it could actually be going by some other conformation. But it certainly shows that pseudo-trans cannot react to produce a Diels Alder product. Now the reaction is also stereospecific. And that's very important to understand when we get into cis-trans isomers on the dienophile. Suppose I have a diene again. And I react it. And we're going to react it this time with 2 different alkenes. One, and let's put an electron withdrawing group, CO2CH3, an ester. And we've got CO2CH3. Okay, so CH3O2C. And let's repeat the reaction with the cis. So Here's H. Here's H. I'll draw it out this time. CO2, CH3 means the ester. Okay, we hit these two reactions with heat. The esters are electron withdrawing. They help speed up the reaction, and we get our alkene, and I'll try to draw it more edge on. What happens is you get the CO2, CH3, one down. The trans gives you trans addition. But the cis gives you cis addition. So the reaction stereospecific. That is, when you do the Diels Alder, if you have a cis alkene, the product is cis. And the reason is all the bonds form at once. Now there is another terminology for this, cis-trans, if you like, addition. And it is usually used when we are talking about the formation of a bicyclic. Okay? And so we're going to look at a Diels Alder reaction now, where two products are formed relative to one another. And we will examine how they form. We're going to take the molecule cyclopentadiene as our pseudo-cis alkene, or pseudo-cis diene. And we're going to use maleic anhydride from a molecular models lab as our dienophile. If you think about it, there's an alkene here with C double bond O's that are electron withdrawing, so that helps accelerate things. Now what's interesting is when we actually react it, the oxygen of maleic anhydride could be pointing either away, or it could actually be pointing towards. Oops, that should be a diene. Now when we apply heat, and both of these happen, it's the same thing. When I'm just showing how the maleic anhydride can come in on the diene. I'm going to use black to indicate the bonds that form. We can get a pericyclic reaction. If we do, we'll still keep this. But we're going to get some new black colored bonds. These are the new bonds that form. Where's my blue? Here we go. Okay. But if it was pointing in the other direction, I would get something that looks like this. Yes, the alkene is the same. This one's harder to see because I'm looking down from the top. This bond actually attaches there, and this bond actually attaches there. And so if you like, this is pointed out and away, and this is pointed into. Let's tilt it and try to look at it edge on. Let's draw this one first. So what I'm going to do is I'm going to draw it this way and put my peak up there. I'm going to still use black to show the bonds that have formed. Okay, so there's my black bonds. Those are the bonds that have formed in the Diels Alder. I will make this fresh so it's in front. And if you like, I'll put in some H's too so you can see where this is pointing. So this guy is pointing up, and you have an H down here. And I'm exaggerating this, H down here. Okay? So this is sort of an edge-on view. We might call this guy exo because the maleic anhydride is pointing out and away from the ring. All right. What about the bottom structure, edge-on? Well, if I was to draw an edge-on view of it, again, use black to show the bonds that formed. There we go. And you see how the maleic is pointed down and underneath. It's almost pointed into the cyclopentane ring. And so this is called endo. Endo and exo are prefixes that are used in naming just like cis and trans. Now what's interesting is the endo is more thermodynamically stable usually. The endo tends to be more stable. And often, because of that stability, he's major. Why would exo be less stable? Well, you see these hydrogens here? These apical hydrogens? There tends to be repulsion between that hydrogen and those electron lone pairs. There is repulsion. Don't have time, space to write it, but there is a repulsion between the H and the lone pairs on the oxygen. And this repulsion raises the energy and disfavors the exo. be really nice if we could think about transition states and see who's more stable. Well, let's try drawing some transition states over here and see if we can guess who would be more stable as a transition state as this guy approaches underneath to make these types of bonds. It takes being able to draw an edge on view, but I'll do that with my cyclopentane. So here's my cyclopentadiene, but instead of drawing, and I'm going to actually make it a little bigger if I can, so I have a little more room to play with when I draw the pi bonds. So let's put in some 2p's. Let's use red. So here's a 2p. Here's a 2p. There's one pi bond. Here's a 2p. And here's a 2p. And the other pi bond. Now underneath it, you have the maleic anhydride coming in. And I will try to line it up. And he has his pi orbitals. Oxygen. And so what's interesting is you get an interaction between those two 2p's, and you get an interaction between those two guys in this one. And so that's what the transition state would look like for the exo. So this is the exo's transition state. Now let's try and compare this exactly to the endo transition state. So I'm going to draw the same thing. Put its 2p's in. And this time, let's look at the endo. So this guy exaggerated a little bit, and let's put in some 2p's. So these two interact. Those are where the bond's going to form. But you see these 2p's right here? They actually, and I'm going to put temporary, I'm going to put green dots. These green dots mean a temporary interaction. There's a temporary interaction between the 2p orbitals here that go out towards the oxygens. So you get the same overlap that you do in the exo as in the endo, but you get some additional interactions. So this is the endo transition state. And these green interactions are referred to as p-orbital assistance. That is, p-orbitals can overlap and in the transition state temporarily interact, stabilizing the transition state. And this p-orbital assistance can stabilize the transition state and lower the energy. And so this suggests, because of p-orbital assistance, the endo is not only the most stable in the final product, but it also has a lower energy transition state. Now, you may be panicking at this moment and saying, do I have to draw that? And the answer is no, but you have to be able to explain it. I will give you the drawings of the exo and endo transition states. What I expect you to do is link up the orbitals and indicate where p-orbital assistance actually occurs. All right? Now, how does this translate into an energy diagram? I'm going to try and fit that on here. It's going to be awfully small. Because you have two products of different stability, okay? And let's again use the most stable one gets black. So I'm going to use the endo will be black. And I'm going to use red for the exo. Do we have to worry about what we learned a little while ago, that kinetic and thermodynamic control? Well, the answer to that, let's say these are my dienes here. Who has the lowest energy? The endo, I'm going to use black. Here's the endo's transition state. The endo is the most stable product, and it also has the lowest energy of activation because it has the most stable transition state. The exo, which is red, is less stable than the endo in final product, and its transition state is higher energy as well. Do we have to worry about kinetic control or thermodynamic control in this reaction? Well, if I look at the potential energy diagram, I don't see any crossover between the two lines. Because there's no crossover, there's no temperature dependence in the sense of generating kinetic and thermodynamic control. There may be some subtle variations in product distribution. So what that means is the endo will be major, no matter what you conduct, because it is more stable. And so if I make these two products, I can indicate who's major. So when I have the reaction, let's just draw it. And I expect you to draw the 3D edge-on view. If I give you this, cyclopentadiene in a reaction, and maleic anhydride, and I say, here's some heat, give me the products, I expect you to draw this. You must be able to draw this. That's better. this is the exo, that's the endo, he's major. He's minor. Okay, so the endo's major because not only is he more stable, his transition state is more stable due to p-orbital assistance. But the situation can quickly become complicated. What do I mean? Well, let's see if I can find an example of that. Hunting we will go. Yes, this should do. What if I do this reaction, but I make some changes? What if instead of cyclopentadiene, I use the molecule furan? And instead of maleic anhydride, I put an NH group here called maleimide. Okay. That means there'll be in the product an oxygen here. So it's the exact same thing. I just changed some groups, right? And down here, I'll get NH. How does that change anything? Well, this molecule was major because he was thermodynamically more stable in the cyclopentadiene gas maleic anhydride. This was caused by repulsion between the lone pairs and a hydrogen. So let's compare this guy to the original structure. I'll draw the original product. Okay, so what I said was these H's here were having a repulsive interaction with the electrons, these lone pair electrons. Around here, there was repulsion here. And this made the exo less stable. So he was minor. Well, let's look at this. Oh yes, okay, well this time all I did was move the lone pair over here. And this H should be close, and there should be repulsion here, right? And there's something very different. The atom who had the hydrogens here was what? What is that atom? That is a carbon. Carbon is not very electronegative. Because it's not electronegative, there's not a huge delta minus delta plus, and net effect is the H has a significant electron cloud around it, and there's repulsion with the lone pair. But nitrogen is electronegative. Nitrogen, because he's electronegative, goes delta minus, sucks electrons away from the H and gets a delta plus. And what's the lone pair? Negative. So we got a lone pair is negative and a delta plus on the H. Whoa, our repulsion is all of a sudden changed to attraction. This is not repulsive. This is attraction. It's hydrogen bonding. Now, attraction or hydrogen bonding stabilizes. there'll be a hydrogen bonding interaction between this hydrogen and that lone pair. That stabilizes him. Okay, big deal. What's the problem with that? Well, let's redraw our original potential energy diagram for this molecule. We had our endo with the lower energy for the transition state, and it gave us the most stable product. Okay. No problem. Now, originally the exo had a less stable transition state, so higher energy, and a less stable product. And so black predominated. Now we're saying, because of hydrogen bonding, this exo gets stabilized more than the endo. So he drops to low energy. So redraw your energy diagram. The transition states are not changed. So I'll redraw my black. Transition states not changed. The stability of the black's not changed. The red transition state's not changed. It's a less stable transition state. But the red becomes more stable. And what is that? Because the exo has been stabilized below the black, the transition state energy has not changed. We see crossover. And what does crossover mean? In the potential energy diagram, it indicates the possibility of temperature dependence in the product. This temperature dependence in the product manifests itself because of low temperatures. You get kinetically controlled reactions. That is where, at low temperature, the black would be followed and the endo would predominate. But at higher temperatures, the exo would predominate. And what are those temperatures? Well, at 25 degrees Celsius, he is major at 25 degrees Celsius. The black line is followed. But as you raise temperature and you go to 90 degrees Celsius, at 90 degrees Celsius, the exo becomes major. Okay, how would you explain this? In the reaction of furan with maleimide, furan with maleimide, because of the presence of hydrogen on electronegative atom, the repulsive interaction in the exo has been changed to an attractive hydrogen bond. This stabilizes the exo, dropping it in energy below the endo. Since there's no change in the p-orbital assistance in the transition state, the more stable exo product has a less stable transition state, and this produces crossover in the energy diagram. This leads to temperature dependence in the products. At low temperatures, kinetic control favors the lower energy of activation of the black. The black endo predominates. So this is the endo product. 25 degrees, the endo is major. But as you raise temperature and you come under thermodynamic control, you start reversing, getting enough energy to go overcome the reverse energy of activation, establishing an equilibrium. Because the biggest reverse is the red begins to build up. Fewer molecules of red get back than the black. And so the red begins to build up as molecules get over and form the red, and red begins to predominate. So that by the time you get to 90 degrees Celsius, the exo, red, is major. So hydrogen bonding messes us up in the furan-maleimide case, giving temperature dependence. And again, this was evident in the potential energy diagram by the crossover of the potential energy or reaction formation diagrams, by the crossover that we observe in those diagrams. Again, you should be able to use kinetic control and thermodynamic control to explain this. And so you have to watch for hydrogen bonding and be able to predict when you're going to get major or minor. Look for a hydrogen off an electronegative atom in the apical positions. Okay? If it's carbon, it's repulsive. If the H is off carbon, it's repulsive. But if there's an oxygen or nitrogen with a hydrogen, that's electronegative. You get hydrogen bonding and it helps stabilize and leads to this thermodynamic and kinetic control. Okay, well, we've covered an awful lot. We've seen a very rich and diverse chemistry for dienes. I'm Dr. Brian Lloyd. This is my Scribblecast, and I thank you for listening.